A function is a set of ordered pairs whereby no two distinct elements have the same first entry. This is basically how a function is defined. And what does this mean? It means that if we call f a function, from definition, you say that it's a set of ordered pairs. This way. Now, if you look at this set of ordered pairs, you find out something unique. This is a binary relation. But in this binary relation, you say that no two distinct elements, this is an element, this is an element, this is an element. No two distinct elements have the same first entry. So a function can also be seen as a special kind of relation. Every function is a subset of a relation, but not all relations are functions, because there may be a relation where, let's say another G, for example, where we have this, I may have something like this. I'll have, you see that this is a relation, but it's not a function. Why? Because this element and this element, they both have the same first entry. So this disqualifies this relation from being a function. So clearly you can say that f is a function, while g is just a relation, but not a function. So this is just how a function is being defined. An entry of each element of this function is called a coordinate. So this is the first coordinate, this is the second coordinate of this element of the function. This is the first coordinate, this is the second coordinate. So these are called coordinates. That is, these entries, they can also be called coordinates. Set of first coordinates are what we call the domain of the function, while the set of second coordinates are what we refer to as the range of the function. Now from this our function we have here now, you see that the set of the first coordinates, which we call the domain of f, is what? The set of the first coordinates. So when we bring this first coordinates together, the first coordinate of every element together here, and form a set, we call this set now the domain of f. Then the range, we say that is the set of second coordinates. The range of f is this set of second coordinates. So it's 1, 9, and 5. So we say that clearly that this function is a mapping from the domain to the codomain. So this is the range of the function, which is the set of second coordinates, and the domain of the function is the set of first coordinate. That's just basically the definition. So if we call this the set that contains this domain, let's say we call it set x, for example. This set is called the source set. Then if we call this one set y, this set here is called the target set. So that a function is a mapping from the source set to the target set. It's written this way: f is a mapping from the source set, which is x here, to the target set, which is y. So this is the most standard way of writing a function. Let's just look at this example. Let x be a set whose elements are map, man, mango, and money. I'll say let y be the set of English alphabets, as this is written now in the set builder notation. I will say let the function f, a mapping from x to y, be the relation that associates with each element of x the first letter of the element. The first question here say, write f as a set of ordered pairs. Find the domain of f. Then finally, find the range of f. From the question presented before us, you see that f is a mapping from x to y, and f is defined such that is a relation that associates with each element of x the first letter of the element. That's the mapping. First question says to write f as an ordered pair. So see that f is equal to the ordered pair man m. We are associating now the first letters. Map the same m. Mango m. Then finally money. Money m. So that the first letters of each element of A is just m. So this is like many to one mapping. That means all these elements of the domain, elements of x, are just mapped to y based on the function, how the function defines them. The domain of f basically the set of first entries: man, map, money, mango. So this is the domain of f. Then the range, see that the range of f is just a singleton set M. So the range, we can see from here that the range is a subset of the what? The codomain, because we define the codomain as the target set. So this range, this is the only element that is being targeted in the codomain. So we call it the what? The range. So now we look into real valid functions of real variables. So say let x be any non-empty subset of R. A function mapping from S to R is called a real valid function defined on a subset S of R, or a real valid function of a real variables. So this is basically what a real valid function of a real variable means. So there are countless numbers of real valid function of real variable, but in this course we are going to be looking at a few most important real valid function of a real variables. And first on our list is the constant function here. Let f mapping from S to R be a function if there is a number k, element of R, such that f of x equals to k for all x elements of S, then f is called a constant function k on S. This basically means that a function mapping from S to R is called a constant function if f of x equal to k for all x in S. That means for any value we can get from this source set, the value of k remains constant. That means the value we have in R always remains constant. The graph of a constant function looks like something this way. If this is our okay, let's call it the y-axis, this is our x-axis. If you have a function, let's say f of x equal to 2, for example, right? That means for any value of x, this graph will just go this way. That this value here is 2, will just go this way. So this is what the constant function means. The function does not, it's just a constant. So this k is just an arbitrary constant. So no matter the value of x in S, the value of k remains constant. That is, the value of k in R always remains constant. So next we have the identity function. This basically means if you have a function mapping from R to R, which is such that the identity of x is equal to x for all x elements of R, then this function is an identity function. An example, and what this thing means is actually, let's say we have the value of x here as 5, a function that behaves such that identity of, let's say, 5 is equal to 5, then this is an identity function. When the value in the source set changes, the value of the target set changes to the exact value of what it is in the source set. So this is what it means, like identical. What this one is, the source set, is what the target set is. So this is how the identity function is being defined. So we can see clearly from here that the domain of the identity function is all real numbers, while the range is still all real numbers, because no matter what it is here, that's exactly what it will be here. So they are both, the domain and the range here are equal. So next we have the signal function, and we define the signal function as a function mapping from R to R whose values at any x in R is -1, 0, or 1, according to whether if x is negative, 0, or positive respectively, is called a signal function and denoted by the symbol xgn. Basically, from the definition, it's trying to say that if you have a function mapping from R to R, and this function is called the signal function, if this function is equal to 1 for all x greater than 0, and is 0 for all x equal to 0, and is -1 for all x less than 0. So this is basically how the signal function is defined. So if you are giving a value, let's say signal of 100, from the definition of signum function, we say that signum 100 is equal to 1. Is equal to 1. And why is it so? It's so because of the definition of the signum function. So if x is greater than 0, in this case here, give the x 100. Since it's greater than 0, the function assigns a value 1 to it. Signum minus 200, what will the value be? We said minus 1. Thank you very much. You got it. So signum 0. Signum of 0 is equal to 0. So this is just how the signum function is defined. So you can see clearly that the domain of the signum function is R, while the range, which is the subset of this codomain, is the set minus 1, 0, and 1. So the signum function has the domain as all real numbers, whereas the range, which is a subset of this codomain, is what? Minus 1, 0, and 1. So you can just basically write the domain of the signum function. The domain of the signum function. So the domain of the signum function, let's say this f is a signum function. So say that dom f is equal to what? All real numbers. While the range of the signum function, that is this function we are dealing with now, is the set minus 1, 0, and 1. So this is basically how the signum function is defined. So let's look into other functions. So next we have the Heaviside function, and we define the Heaviside function thus: the function mapping from R to R whose values at any positive real number is 1 and whose values at any other real number is 0 is called the Heaviside function, and it is denoted by the letter H. So this Heaviside function is basically saying if you have a function denoted by H which maps from the real number to the real number, and this function is such that the Heaviside of x is given by 1 if x is greater than 0, that is positive real number, that's 1, and is given by 0 if, or we can say 0 otherwise, that means if it's not greater than 0, or we can just say 0 if x is less than or equal to 0. So a function of this form is what we refer to as the Heaviside function, and this is basically saying if you have an x which is greater than 0, we assign the number, the function assign the number 1. So this is just like a refinement of the signal function. In this case here, if you have anything minus the Heaviside of minus 10, it will be what? 0. Remember what signal function says. If it's for signal function, signal of minus 10 is what? Minus 1, yes. So but in this Heaviside function, anything less than or equal to 0, the Heaviside function assigns 0 to it. But anything greater than 0, it assigns what? The number 1. So you can see from here that the domain of the signum function, the domain of the Heaviside function is all real numbers, while the range is 0 and 1, because for any number, any real number you plug into the Heaviside function, the output will only be either 0 or 1. So that's basically how the Heaviside function is defined, and this for all x elements of R. So that the domain of is what? All real numbers, while the range of the Heaviside function is just 0, 1. This is the range, these two elements are the members of the range of the Heaviside function. So next we have the modulus function, which is also called the absolute value function. This function is represented by mod, or the absolute value, and it is being defined as the mod of x is being defined as this: x if x is greater than 0, 0 if x is equal to 0, and minus x if x is less than 0. So this is basically how the modulus function is being defined. So what does this thing mean? Let's say we are given, for example, the modulus of 10 from this definition, you see that the modulus of 10 is what? 10. From this definition, say x is greater than 0, so it will be x, which is this. 10 is greater than 0, so the modulus of it will be 10. Then if you have the modulus of minus 10, for example, the definition says that the modulus of minus 10 is given as what? Minus x. Now, you have to pay close attention. This thing means minus 10, because this our x here. You see, if x is less than 0, we give it this sign. So it's like multiplying the negative to the negative number. So basically, this absolute value function takes away negativity. That means when there's a negativity, the modulus function makes it what? Positive. So it is also called a distance function, because a distance, you cannot have like a negative distance. So that's why this function is very, very important, because it takes away every negativity. Let's say you have modulus of, or it can be written this way, the absolute value of minus 3 is given by what? 3. Why? Because this definition says absolute value minus 3 is equal to minus 3, which is equal to 3. So basically what this function does is that it takes away every negativity. Where something is negative, it makes it positive. Where it is positive, it remains positive. And where it is 0, it's still equal to 0. So from this, we can see that the domain of the absolute value function, domain of this function, the absolute value function is what? All real numbers. Why the range are the possible outcomes. The range of this function is 0 union the positive real number, because it is 0 when the value of x is 0 and every other place is positive. So you can just say that they are given as this 0 to infinity. So this is the range. Why the domain, you can say negative infinity to infinity. So this is basically how the modulus function operates. Next we have the greatest integer function. For me, this is the most interesting real valued function of real variables we are going to look into in this course. And it is very interesting because it has to do with step. It also is a special case of the step functions, and define it as the greatest integer function is a function that maps a real number to the greatest integer less than or equal to it, and is denoted by the square brackets. It can also be represented as the maximum of n, an integer, such that n is less than or equal to x. So this basically means if you have the greatest integer of x, can be represented as the maximum value of n, that is an integer, such that n is less than or equal to x. So it is equal to x when n itself is an integer. But if n is not an integer, then the value of the greatest integer of x is the greatest integer that is less than or equal to that x. What this means is that if I have a number like 2, for example, the greatest integer of 2 is equal to 2, because from definition it is the greatest integer less than or equal to 2. Because this 2 is an integer, the greatest integer of 2 will be what? 2. Now if you come for the case of the greatest integer of 1.9, the greatest integer of 1.9 is the greatest integer that is less than 1.9, which is equal to what? 1. Now the greatest integer of 0.5, the greatest integer of it is what? Because this is not an integer, the greatest integer of it will be what? 0. The greatest integer less than this. Now what of the greatest integer of minus 0.5? This is where things get interesting. The greatest integer of minus 0.5 is what? Minus 1. Why is this so? Because the greatest integer less than minus 5 is minus 1. Now most people confuse these things, but if you understand the number line very well, you will not find it difficult to understand it, because when you look at this 0.5, for example, if this is our number line and here is 0, here is 0.5, here is minus 0.5, here is minus 1, that is in the number line, here is 1. Now if you take the greatest integer of this minus 0.5 from definition, we say that is the greatest integer that is less than this, because this is not an integer. So the greatest integer less than it will be what? 1. Minus 1. So integers are both the positive and the negative whole numbers, including 0. So the greatest integer of this one that is not an integer will be what? -1. And the greatest integer of -1 is what? -1, because -1 is an integer. The greatest integer of 0.5 is this way. So it just go, either it remains that place or it goes backward to the greatest integer. The big hint there is to understand this number line, so that whenever you see a question, you'll be able to tell which one is to the left of it, that is the greatest integer that is less than it. So that's basically what the greatest integer function is all about. So you can clearly see that the domain of this function, the domain of the greatest integer function, domain of this function is what? All in numbers. You see that? Why the range? The range is what? The integers. So that's just how this function operates. So next here we have the linear function. I will say let a and b be any real numbers. The function f from mapping from R to R, whose values for any x in R is given by f of x equal to ax plus b, is called the linear function. So this basically means if you have a function mapping from R to R, I will have constant a, b, elements of R, that the function which is denoted as this. Okay, let's say ax plus b. This is called the linear function. If you look very well, this is a linear equation. It can be the form of, let's say, f of x equal to 3x minus 5, or f of x equals to 14x plus 2. So this is an example of a linear function. This is just the domain of the linear function is all real numbers, while the range is still all real numbers. Now there is a special case of the linear function which we call the affine function, and in this case is when the intercept, that is this factor here, is 0. That means if you have a function f of x equal to ax, this is a special case of the linear function which we refer to as the affine function. So the graph of the linear function is just a straight line graph that cuts the x and y axis at two distinct points. But in the case of the affine function, the graph is plotted through the origin, because when you plot the graph of this function, you see that the graph cross, that is the origin, pass through the origin. So it's just like a special case of the linear function. So these two functions, in quotes, they are special cases of the polynomial function. That means a polynomial of degree 1 is a linear function. So let's look at the polynomial function proper. The polynomial function is an important class of functions that may be generated by operations on the constant function and identity function. A polynomial function of degree n, denoted by p mapping from R to R, is given by this. So this is a polynomial function of degree n. So a sub n raised to power n plus a sub n minus 1. These a's are constant, x raised to power n minus 1. Okay, let's a sub n minus 2 x raised to power n minus 2, and it may continue this way, plus a sub 1x plus a naught. So this is a polynomial function of degree n. These a's are constants, while these x are variable. This is the degree. So in the case of the linear function, you can see clearly that when our n is equal to 1, we have a function of this form. A, that is this, a sub 1x plus a naught. So this can be called, this is a linear function. Or the normal quadratic equation you solve is from this polynomial function. That is when the degree is what? 2. You get the quadratic function. So all of them are just gotten from this polynomial function. So here we see where n is an element of what? A natural number. So n can be 0, 1, 2, 3. If n is 0, we have the constant function. If n is 1, we have the linear function. If n is 2, we have the quadratic function, and so on. So n is just an element of the natural numbers. The rational function, like the name implies, it is a ratio of functions. So we're giving polynomial functions p and q mapping from r to r of degrees m and n respectively, and q is not the constant function, then the function r, which is the quotient of p by q, is called a rational function. This implies that if you have a function which is r mapping from r to r, where this is represented by p q of x, such that q is not equal to 0 if both of them are both polynomial functions and they are equal to r in this form, then we say that r is a rational function. So mostly this function are seen in terms of when we want to resolve into partial fraction. We encounter the rational function mostly in such cases. So finally we look at the root functions. So here we say that the root function for any non-negative real number a, its nth root is denoted by nth root of a is defined as a non-negative number b, such that b to the power n equal to a. What this root function is saying is that if you have a function which we define as this, which is the nth root of a, this is a, it can be written as this, and it is equal to, this is equal to a number b, such that b to the power n is equal to a. For example, if we have a function f of x and we are looking for the cube root of x, for example, so this goes to y, such that y raised to the power 3 is equal to x, then this is called a, this is just a simple example of a root function. So in this case now, if we have our x as 8, for example, so the cube root of 8 will be what? Will be a number which we know is what? 2. And if you see 2 raised to the power 3 is equal to what? 8. So this is what the root function entails. Note that if a is negative, there is no even nth root of a in r. However, there is this odd nth root of a negative number given by nth root of a is equal to negative nth root of negative a for a less than 0 and n odd. So this means that if a is less than 0 and n is odd, then the nth root of a is the negative of the nth root of minus a. So this is trying to tell us that if we are looking for the nth root of a negative number, for example, nth root of, let's say, minus a, this is not, there's no solution for this in r if this n is even. Let's say you are looking for the square root, for example, of minus 2. This is not in r. Remember, we are dealing with real value function of a real variable. This particular function here, this particular number here is not an element of the real number, because we know that the square root of minus 1 is what? An imaginary number. Now if you are dealing with an odd n, for example, let's say you are looking for the cube root of negative a, right? You say that this will be equal to the negative of the cube root of a, because this is not an even number, this is an odd number. So this is what is equivalent to b, because that's what this root function is trying to tell us. For example, if we have our a as, let's say, 27, for example, the cube root of minus 27 will be equal to the negative of the cube root of 27. So this one we can quickly solve. The cube root of 27 is what? Is equal to what? 3. So we have our answer as what? Negative 3. So if you multiply this thing to the power of 3, you see that it will give us this number here. So in summary, you cannot find the even root of a negative number. That's what we're trying to say. You cannot find the event root of a negative number. That is, when n is even, the nth root of a negative number is not an element of the real number. But when n is odd, the nth root of that negative number can be expressed using this notation from the root function. So this is basically a few pre-valid functions you're able to look at here. So in this video here, we looked at examples of function that puts this function, some of these functions we have studied here together and as one function. That means you can have the polynomial function and the root function together as a single function. Then we show how to find the domain and range of such function. So thank you very much for watching. I'll see you in the next video.